All right, let's begin. So what we have is we have this little problem here, which is the last problem in 1.9, and hopefully we can finish this off. And just to give a little bit more context information that we can kind of normally do in the last 2 minutes of class. So let's go with it here. So I have this function, and it talks about diesel mechanics or diesel engines. So I have these conditions. So approximate the exhaust temperature Y in degrees Fahrenheit. Okay, where X is the percent load for a diesel engine. So let's talk about what this even means. Let's go with it here. So load on the engine is just how much power it's using to go higher than its normal. So looks like if there's no load on the engine, it's running idle. So if I put a zero into there, and then it goes all the way up, and it's not actually, like, interestingly enough, it's not exactly a zero less than or equal to X. It's actually less than X, which is less than 100. So not going fully, not breaking the engine, but really climbing up to the highest level it could. Okay, so then if the engine is idle, we got that. And then we have, let's see, find the inverse function. What does each say? Graph utility, perfect. What is the percent load interval? Okay, let's jam. First things first is, so notice that this is my equation that takes the percent load, which is X, and returns the temperature. So it goes from load to temperature. What I want to do before I even start the inverse function, because we're going to have to give the domain for the inverse function anyways, I'm going to plug in a zero into this and just sort of see what is happening here. So if I were to plug in zero into this function, that will give me my base temperature. And it's because of that zero right there. That'll give me my base temperature for this. So this engine runs at 245.5 degrees Fahrenheit as a idle engine running. So then when I put in 100% load, getting this engine to go as tough as it can, I'm going to square that, add 245. I'm going to see what the temperature is according to this model. What is that? So let's see, 100 times 100 is 10,000. 10,000.0.03 is 300. Plus 245.50, and voila. So here's what I have. I have the hottest this thing goes is 545.5 degrees Fahrenheit. Okay, so that was the Y. We plugged in the lowest value for Y and the highest value. Oh, sorry, lowest value for X, highest value for X. So now that was the lowest point in the temperature scale and the highest point. That corresponded to X equals 0, and this one went to X equals 100. So what I know is this. I know that 245.50 would be less than Y, less than 545.50. Are we good there? So those correspond. So that 0 corresponds to the 245.50. The Y the X corresponds to the Y this time, and the 100 would correspond to the highest temperature goes. Cool. Okay, so now we're going to create a different function. We're going to create the inverse function. So let's jam. Hey, here it is. Here's my original function from the previous slide. And now what do we do to create an inverse function? We change X's and Y's. There it is. Let's substitute or interchange X's and Y's. And let's do some math. So subtract 245.50, 245.50. Voila, that's gone. X minus 245.50 here. And then we're left with a 0.03 y squared. We are going to divide by 0.03, 0.03. And that is going to cancel that off. So let's just have y squared on one side. I just switched them. It just looks a little better when you have the variable is solving for on the left-hand side. And we are going to do one last thing. We are going to take a square root here and a square root here. We're going to only use the positive. We're not going to do plus and minus. We're only going to take the positive square root because we don't do negative temperature for Fahrenheit. Okay, so if that is the case, here's the final inverse function right there. And I've created it. All right, it does have a domain. The domain restriction for this guy is the range restriction from the function itself. So notice the only thing that's changed from the previous slide is I exchanged the X's and the Y's right there. There it is. So to use this function right here, the range can only work from 245.50 degrees to only to 545.50. I cannot use this function for 600 degrees, 700 degrees, 800 degrees. It will not work there. Okay, so now it says what do the variables mean? In this case now, X is the temperature, the input value is the temperature, the output is the percent of load. So now we have two equations if you think about it. Now the first one takes the load and gives us temperature. This one actually takes temperature and gives us load. That's what we want to see. We want to see the fact that we've created two different functions. All right, so hopefully that makes sense. Let's move on to part B. Part B actually says graph this on a calculator. So let me do this here. Let me get off of there, go to here. Okay, so let's do that. Let's go. Let's jam now. We are going to go y equals, and we're going to have to plug in that inverse function. So a few things here we're going to do. There's the square root, which is down here. This is the second function. And notice we have x minus 245.50 on top. So what we're going to have to do is we have to put an extra parenthesis because we want to keep the numerator on top, 245.50. And then we're going to use that as that's the numerator. We're going to divide that out by the denominator, 0.03. And then we're going to close off. This parenthesis actually to close off the square root. So there it is, boom. Okay, now we've noticed that our domain, remember our domain for this guy is from 245.50 to 545.50. So we're not going to just put the graph function, because if we do that, our graph function only works from -10 to, in fact, let's click to the little window button right here. The way our screen is looking, our window's looking is from -10 to 10. We're not even going to get any function inside here. So since we're graphing the inverse function, we want to go from 245.50. And let's leave an extra little room there. That's what we want to do. Leave an extra little room from the 245.50 there. I'm going to go 200. So I'm going to go 200. And 545 is it? So I'm going to go up to 600. And the tick marks, you can do maybe like every 20 or maybe every 50. So that's kind of what we want to see. So temperature is from, we're going to look at temperature from 200 to 600. And then for the y value, oh, that one's going to be 0 to 100, right? But we want to give a little bit of a gap there. So I'm going to go maybe like -10 to 110. And then let's go by tens. Okay, that's going to give us a window, which we'll be able to see the graph itself. So 245 was our minimum. We went a little bit below that. 545 was our maximum. We went below that. And our tick marks is the little tick marks you see on the bottom of the calculator there. So I think we got it right. Let's graph this guy. And graph. Yes, there it is. So now this gives us temperature to load, where the original function was load to temperature. So there it is. That little tick mark, let's see, if that's 200. So that was 250. This little tick mark is 250. Yeah, and 245.50 is about right there. That's 300 here, 350. 450, 550, and 600 is right at the end here. So, and then the load starts off at supposedly almost like a 0 here, right? And then it kind of starts climbing up. There it is. Okay, so that one, hopefully that was useful to you. Okay, so part C, it says, oh yeah, it says if, what's the range for the load if the temperature cannot go above 500 degrees. So for some reason, maybe the bearings can't handle more than 500 degrees. Maybe there's something in the engine there that actually does not allow it, or it's going to start breaking. Certain things are going to start breaking there. And so we need the temperature to be less than 500. Okay, so remember, we have two different equations. One takes load to temperature. That's the original function. One takes temperature to load. So the one I need to use is this one right here. I'm going to use the inverse function because that's the one that gives me what I want. All right, so we know a few things here. So remember the base temperature is 245, right? 50, that's the lowest it's going to go. And 500 obviously is less than 500. So our input value is here. And our output value for the 100% load was right here, right? So that's the one we want to actually bring down. So first things first, if X was equal to 245, how much load do we have? That's the little bottom temperature, right? So we're trying to develop the load range. We plug in the lowest this guy can go. And obviously, as we've been talking about this already here, this guy's going to become a zero, obviously. So notice the temperature of 245.50 gives us an output value of 0 load. And now this one's going to be the Y value, right? For us, Y value is the load. So now instead of putting in 545.50, we're going to plug in the 500. So if X is equal to 500, what would be the load on this engine? So 500 minus 245.50 over 0.03, punch this into your calculator, and you should get 992 point, I think it's like 1.05 or something else like that. I did it real quick here before. Let me see if I can, let's use our calculator again. Boom, let's go to quit. Let's go to here and let's go with, let's see, 500 minus 245.50, enter. We're going to divide this guy by 0.03, voila. And then we're going to take the square root of this guy. So the way you do a square root is that you can get second function. And the nifty little thing is, notice over here you have something called ANS. So it just means answer. So your previous answer. So what you do is you go click second function, answer. So you don't have to type that in all over again. Close off the square root, click enter, and there it is, 92.105. Yes, that's perfect. Okay, so rounding it off, the back of the book did, we're going to go to 92.11, and that's going to be the highest load that we can have without it going above a temperature. So then that should be included right here, 92.11. All right, hopefully that was useful.